rules. Now, these basic rules that are so messy on here, that's what I've rewritten very nicely on that reference sheet. So I rewrote these basic rules, but we had exponential functions where the input was going into the exponent, and we had log functions where the input was going into the argument of a log. And we did some basic problems, but the main issue students usually have with these rules is with logs, is with reading log notation. I know in college algebra, logs are like the bane of everyone's existence. So we're going to practice today reading log notation with these derivative rules. So I think we stopped here. Okay. And I'm going to cover our first log rule that from college algebra that's going to be really helpful in this class, but it is not necessary. So what I'm about to show you is helpful, but not required. So if you're really iffy on your algebra rules, you can just do calculus. You do not have to do what I'm about to show you. Okay, but I'm going to show it to you just in case you remember. So up here in this little box, this is a log rule from algebra. So we're going to do a little we're going to algebra land right now. Okay, so we made logs up, just like we made up square root signs, just like we made up addition signs. Log is just a symbol. When you see LOG, LOG is a symbol that tells us we have a job to do, okay? It's just a symbol we made up. And the job is to reverse, to undo exponentials. So log functions and exponential functions are inverse functions. They undo each other, okay? So because of that, we have this rule in algebra that says this. Okay, it says if you have a log, you're taking the log of something, it can be a natural log. So it can be a natural log or an LOG log. But if you're taking the log of a base that has an exponent on it, so if the argument involves a base with an exponent on it, okay, in any form, what the rule tells us we can do is we can rewrite the log by dropping the exponent in front of the log. So we write the exponent in front of the log, and then you would just rewrite the log with the base there. So this is just algebra. So let's see an example of this. So if I had natural log of x squared, natural log of x squared. What the rule says is since I have a base, x, with an exponent 2, the algebra says I can drop that 2 to the front, and an equivalent way to write this is 2 natural log of x. And I just want to emphasize this is not the power rule, it's a log rule. So this is an algebra rule, not calculus or power rule, because students start getting them confused. Calculus / power rule. What I'll see students do is they drop this exponent down and then they want to decrease the exponent by 1 and do all kinds of stuff. We are not doing calculus right now. This is just algebra. Okay, so show me either a status or like an agree or a happy face or something on your status. Do you remember this log rule from algebra where you could drop the exponent down in front of the log? Okay. So some people are remembering, some people are like, yeah, it was a blur. Okay. So the good news is you do not need to know this algebra rule. It's just super helpful. So we're going to work a problem where we're going to use the algebra rule to get the derivative, and then we're going to do no algebra rule and just do calculus, and we're going to get the exact same answer. So if on the day of the test you're like, I don't really know if I can use this algebra rule, don't use it. Just do the calculus, or do both ways I'm about to show you and make sure your answers match. And if they don't, go to the calculus, okay? So let's look at this problem here. So our function takes an input, and it puts our input into an argument, into this x to the 4th. So the standard way to write this log is without parentheses around the argument, but there are understood parentheses around that argument. I'm taking the log of x to the 4th. That 4 is attached to the x. The 4 works on what it's immediately directly touching. If that wasn't the case, it would look like this down here on B. See how in this problem, the 4 is immediately touching the parentheses, and the parentheses is working on everything inside, the whole log x? Like, you just have to slow your brain down and read the notation. So we'll work B in a minute, but coming back up here to A, there's these understood parentheses around that x to the 4th. So x to the 4th is the argument. Okay, so we're going to find this derivative 2 ways. So method 1, for method 1, I'm going to rewrite this using a log rule. So rewrite f of x using a log rule from algebra. Algebra. Okay, so let's do that. Here we go. Okay, so I'm going to take my function, f of x equals natural log x to the 4th. And I'm just doing algebra here. So I'm going to keep my f of x notation. I'm going to keep my f of x notation there. I'm just doing algebra. My log rule says if my argument has an exponent, I can drop the exponent to the front of the log and then rewrite the log and the base. So this is algebra. But then look how nice that is. See how my function, this ln of a plane x, matches that really basic rule right there, ln of the plane x, where the derivative of the x is just a 1, right? The derivative of the argument of a plane x is just a 1. So it fits that rule really nicely. The only difference is in your generic rule that my MATLAB shows you, there's an understood 1 in front of the log. If nothing's written, it's an understood 1, and there ends up being a 1 in that numerator. So what I did on the reference sheet was I rewrote that. I said, if you're taking the derivative of a log, ln of x, a natural log, and there's a constant in front, then when you do all the algebra, the constant ends up in the numerator. So you can think about this function 2 ways. When you go to take this derivative, that 4 is along for the ride, and then the ln of x turns into the 1 over x. But isn't that 4 just a whole number, so we put it over a 1? And when we multiply it across, doesn't that 4 just end up in the numerator? So once you do enough of these, you can train yourself to see that that 4 in front of the ln of x is just going to end up in the numerator. And technically, we're tacking on the derivative of the argument, but the argument to plane x and the derivative of x is a 1. So we don't really need chain rule when your argument's just a plain everyday variable. So my derivative for this one is just going to be 4x. Sorry, 4 over x. So let me pause here. Give me a status. How do you feel about finding that derivative with that algebra rule? Or you can raise your hand if you're typing or want to ask a question. And again, these are just rules you're memorizing. If you really want to prove the rules to yourself, you can do 4-step process and take the limit of the difference quotient, but I'm not going to do that. Okay. So no one's raised their hand for a question. So let's see this. Let's pretend we didn't know the algebra rule. I'm going to shrink this down. Now we're going to do method 2. We're just going to work with the function the way it was given to us. Okay, so now we're going to do method 2 here. Here we go. Method 2. We're going to just work with this function as is. So method 2. We're going to take derivative as is. We're not going to rewrite it. And we're going to get the exact same answer. So I'm going to take this function, natural log of x to the 4th. Okay. And I'm going to use my ln of x rule, but in this case, my argument is not a plane x. So the argument is not plane x. So we must use the chain rule. We don't have a choice. We must use it in this case. We can always use it, but in this case, we have to use it. So let's go ahead and do our derivative. So my derivative says, what does the rule say in general? The rule says in general that if your function is natural log of x, the derivative sends the argument to the denominator. So my derivative is going to send my argument, x to the fourth to the denominator, but then I have to tack on the derivative of the argument. Then you tack on the derivative of the argument there. Okay, so I need to do derivative of the argument. Okay, so let's go ahead and do that. So f prime of x equals 1 over the argument times the derivative of the argument. You just do power rule for this. Plain old power rule. The base is a plain x, so it's really straightforward. 4x cubed. Technically times the derivative of the base, which is just a 1, so I'm not going to write it. Okay. And then we're going to clean this up, because remember, it's supposed to look like 4 over x, and right now it does not. But I can just put that 4x cubed over a 1, and then when I multiply across, that's going to give me 4x cubed over x to the fourth. And do you see where it's going? See how there's x's in the numerator and x's in the denominator? And those x's are going to simplify, they're going to divide out. So let's go ahead and do that. Let's go ahead and simplify that. The 4's in the numerator, if there's 3 factors of x in the numerator and 4 in the bottom, and I divide them all out, there's 1 x left in the denominator, and I get that exact same answer using my chain rule. One way is not better than the other. If you didn't rewrite with your rule from algebra, you had a little bit more work to do, but not much. So I'm going to send out a poll real quick. I'm just curious who prefers method 1 with the algebra versus method 2. So I'm just going to send that out real quick. Here we go. Oh, Jocelyn, sorry, I didn't see your hand was up. You have a question?
I already put it in the chat.
Oh, you did? Oh, I'm sorry. For some reason, I'm not hearing much. My volume is a little low, So Jocelyn, there's only one rule, derivative rule, that I'm using for this function. So because my original function has a natural log in it, I have to use the natural log rule. That's the only rule I can use. But because the argument of the function is not a plain variable, it's not just a plain old x, this is a quartic function. Because my argument is not a plain x, it's a composition of functions. So I have to do chain rule, which is what I did here in method 2, or if you know some algebra, you could do method 1. Method 1 says if you know an algebra rule, you can drop that exponent down, and then it gives you the natural log of a plain everyday x, which follows our basic rule exactly. So technically, I'm only using one calculus rule here. I'm using the calculus rule for natural log, but I thought about it 2 different ways. So if you're really comfortable with algebra rules, with log rules, you can rewrite this and make your life a little easier. If not, that's okay. Just do the calculus. And you're going to end up with the same answer. You just have to be kind of careful. I don't know. Did that answer your question, Jocelyn?
Yeah.
Okay. So let me send out a poll because I'm just curious real quick, which method did you prefer? So I'm sending this out. Did you prefer? Okay, here we go. Method 1 or method 2. Okay, here it goes. It should be coming up. Okay. Ooh, it's pretty close. Oh, wait. Okay, method 1 is winning out. If you know that algebra rule, method 1 is... Okay, I think method 1 won. Okay, so you like the algebra. So I will keep doing that algebra rule, but could you do the chain rule? Yes. Okay. I won't have time to do both every time, but so if we're leaning towards method 1 with the algebra rule, I'll keep reinforcing that algebra rule. Okay. Now let's look at B, because B is a little bit different. I see a log, right? So I'm all excited. I see a log. So we know we're like log rule all the way. But let's read this a little bit more carefully here. When I look at the input into this equation, or into this function, the input is coming here in this argument, but this argument is part of a base. It's a base with a constant exponent. If your function is set up where the input's going to any base, and that base is a constant has a constant exponent, then you're going to do power rule. So this one is actually set up for power rule, but we're going to have to use the chain rule because is that down? Base is not plain x. The base is a function. So since that base is a function, we have to do power rule with the chain rule. Okay, so let's see what I mean by that. Here we go. Let's just take our derivative. Oh, and just heads up, I cannot do the log rule on this, so let me write that down. So can't use algebra, log rule from algebra. Because, why can't we use log rule from algebra? So let me rewrite this. Okay, so here's what I was given. I cannot use the log rule from algebra because is that exponent working on my argument? No, what's the exponent on this argument is technically a 1, not a 4. So I can't use it because the exponent is not connected to the argument. So the exponent, how do I say it? Does not directly affect the argument. It's not attached to the argument. So I have to use power rule with chain rule. I can't just drop that exponent down and rewrite it. Here we go. Okay, so let's go ahead and do that. So I'm starting my calculus because I'm going straight into my power rule. My power rule says I take the exponent, I drop it down to the front. So I'm going to drop my 4 to the front. I rewrite the base exactly how I see it. My base is this ugly thing, but I'm just going to rewrite it because that's what power rule says. Then I decrease the exponent by 1. This is power rule. Power rule says to decrease the exponent by 1. Then I tack on the derivative of the base. So let me pause there to see if there's any questions on how I applied the power rule with the chain rule. Give me a status so I can see how you're feeling up till right now. We've got a lot of shocks right off the bat. It's all about learning to read the notation. A lot of shocks. Okay, so if you're one of the people who's shocked right now, that's okay. Let's write down in words why we need the power rule. So the reason why we need the power rule is the exponent is working on a base, like an entire base. So let me write that down. So the exponent is, how do I say, directly touching an entire base. Does that make sense? I don't know. I'm trying to write it in like English words. So the exponent is directly touching the parentheses, or directly touching the base inside the parentheses. I'll just put base / parentheses. So this is power. So if I had given you this function, f of x equals something to the 4th, and I had put like x minus 3, no one would have batted an eye, right? If I gave you this, you would have been like, oh, my input went to a base. The base has a constant exponent. A constant exponent. So you're like, oh, I do my power rule. You wouldn't have thought twice, right? You would have just done your power rule with chain rule. The same thing's happening here, except I made my base a little uglier. I made the base a different function. I made it a log function instead of a nice, pretty linear function. Like originally, I put a nice linear function there as my base. I made you comfortable, right? You didn't freak out. All I did was replace the base with a log function, and then our brains freak out. But you're going to slow your brain down. Okay, go ahead. Jocelyn said she doesn't, she has a question why multiplied by the derivative of the base. So our fundamental rule for any derivative is if your function is involving a composite function. So if your function is composite, that means you plugged a function into a function. It's a more complicated function. Then you have to take the derivative of that composite function. So for example, for the log rule, the basic function would be taking a log of it every day x. But if I replace that x with something like x to the fourth, now I have to do chain rule. Or for something more familiar, if my function was linear, or let's say quadratic. If my function's quadratic, we all know the derivative of this is just 2x. Technically, I'm tacking on the derivative of the base, but if my base is a plain everyday x, then the derivative of that is just a 1. But if I take that function and I compose it, and maybe I put a linear function into the quadratic function, see how now my base is more complicated? It's not a plain x. Then when I take the derivative of this, I follow my power rule, but I have to tack on the derivative of the base. Now it's required to tack on the derivative of the base. And in this case, the derivative of this base, that was a bad example. Let me put a 5 in front. The derivative of this base is going to be 5. So when it's a plain everyday x, the derivative is just a 1. So it's like you don't really need to do it, but you are doing it. It's just not required. If your base is more complicated, you have to. Same thing goes with logs. If your argument is more complicated than a plain x, you have to do chain rule. And chain rule says you tack on the derivative of that composite function. In the log case, it's the argument that's composite. And if you're struggling with this, make sure you watch some videos this weekend about composite functions. I know it's a prerequisite from college algebra and you're supposed to know it, but we might need to dust the cobwebs off. So, watch some videos, look at your old notes from college algebra about composite functions, and that'll help you here with this chain rule. Okay, let's go ahead and look, speaking of that, let's go ahead and look at C here. This is a composite function, y'all. So just so you know, this function originally looked something like this. The base function is the parent function. Remember parent functions from college algebra? The parent function is ln of x. But then there was another function that said 4x that was linear. And what they did here, let me make this a different letter here. Let's make that h. So what they did is they created a new function f, and they said to create f, we're going to plug g into h. We're going to plug g into h. Well, if I plug g into h, if I come up here to my h function and I plug g into it, okay, if I plug g into h and g is just the rule for x, then I plug a 4x in there. See how I made this composite function? I replaced the parent function with a generic x for your argument with something more complicated for the argument. That's how I know I need to use chain rule. So let's go ahead and do this. This is going to be the log rule, but with a chain rule. And there's no algebra you can do to clean this up. There's no exponent on the base or anything. We're just going to have to do our log rule, so the ln rule with chain rule. So let's go ahead and do it. So what does my basic log rule say? My basic log rule, I wrote it over here. The basic log rule. Oh, and I meant to rewrite this one with the function notation. Your rule actually looks like this. If you're taking the log of something where the argument's a function, then you want to do 1 over the argument, which is a function, times the derivative of the argument. That's what that rule looks like with that composite notation. I meant to go back and rewrite that. So here we go. So my derivative rule sends the argument, this is my argument. My argument is x to the 4th. Oh, go ahead. Oh, sorry. Yes, I got sidetracked, Shayla. We did not finish part B. Let me finish C since I already got this far. And we'll go back. We did not finish B. Like plus a million points to you. I got all caught up in that and I didn't do it. Maybe we should just finish B now. Well, no, we're already halfway there. Okay, let's finish. Let's get this one set up because this one's a lot faster. So here we go. Okay, so my argument is 4x. So my derivative rule says the derivative is 1 over the argument. What was my argument? My argument was 4x times the derivative of the argument. And that's where I stopped up here on B. What's the derivative of my argument? So let's go ahead and do that. So that's going to be 1 over 4x times, for my argument, it's a linear function. So I'm just going to follow power rule. And the derivative of 4x is just 4. Okay, well now let's clean that up. That's my raw derivative. That 4 is technically a fraction, so I can put it over a 1. And then numerator times numerator, denominator times denominator, that's going to give me 4 over 4x. And then my 4s are just going to divide out to be a 1. But that x is in the denominator, so it's going to stay there. I'll put a 1 placeholder in the numerator, and that x is going to stay in the denominator. So I did my log rule with the chain rule where I had to tack on the derivative of the argument. Okay, and let's go back and finish that one I didn't finish. Whoops. I'd only get half the points on my test. No, we don't want that. We want all the points. Okay, here we go. Let me refresh my brain here. Oh yeah, so B was the one where you had to do the power rule because the exponent was working on a base. So I dropped my exponent down, I rewrote the base, I decreased the exponent by 1, and then I tacked on the derivative of the base. Okay, so now we just have to take the derivative of the base, right? So let's go ahead and do that. Let's shrink this down a little bit so I have some room. Okay, so shrink that down. Okay, so here we go. Let's go ahead and finish that one. So my derivative is 4. Rewrite the base. Decrease the exponent by 1. And the derivative of ln of x, that fits my basic rule exactly. It's just 1 over x. Technically times the derivative of the argument, but the base is a plain x, so that derivative is 1. Okay. I promise I'll stop saying that at some time, but right now we're still learning. So now when I go to rewrite this, it's just going to be hideously ugly, y'all. This is just nasty. Technically, this 4 I can put over a 1, and the base I can put over a 1. So all that's in the numerator. So I multiply all that to the numerator, and that x just stays in the denominator. So as ugly as it is, your answer for this is going to be 4 base cubed all over x. That's your yucky, horrible derivative. Shayla, did you get that when you finished it earlier? Or I don't know, maybe you didn't finish it. Yay, you got it. High five. I'm sending you a high five through the computer. You can't see it, but high five. Everything is scary the first time you see it, y'all. Everything is scary. And then you just have to practice it. And the real learning doesn't happen here in the classroom. I wish I could take credit for all your learning. But it happens when you're struggling on your homework. Luckily, the human brain is programmed to learn from mistakes, right? So you're going to mess up, and then your brain has to figure out why you messed up. And here's the thing with training your brain when you're doing your homework. If you made a mistake for some reason, when you initially did that mistake, it made sense to you. You have to convince your brain why that mistake did not work. Why that mistake was wrong. If you cannot convince your brain why that mistake was incorrect, then you're going to keep doing it. And sometimes you can convince yourself why it was wrong. Sometimes it's a silly mistake. Sometimes you can just think about it more and be like, oh, that's why. Sometimes you need help. That's why you come to office hours. That's why you go see Madhavi Pratapar, an amazing instructional associate. She's only available during the week. Or you go to the Learning Lab, or you can use those 5 free hours of BrainFuse tutoring 24 hours a day, 7 days a week, if the office hours times don't work for you. But yeah, so you have to convince yourself why that mistake was wrong because your brain thought it was right. So you got to tell yourself it was wrong. This is why. Here's the right way to do it. And this is why. Okay. It takes time. It takes time. Doesn't take a super high IQ. It just takes time. So make sure you're giving yourself time here. Okay, up until now, we've just been doing the e to the x rule and the ln of x rule because those rules come up the most in later sections when we do more complicated business formulas. Now we're going to practice some of the other rules, the base B rule and the LOG rule. We're going to practice those. Oh, go ahead.
Priscilla had a question.
Yeah, go ahead. Oh, in the chat? Oh, sorry. Why am I not hearing the chat questions? Let me come back here. Oh, sorry. So Jade asked to go through part B again. Will do. And Priscilla said, I did not get the derivative part. Okay, cool. So let's go back and look at that. Sorry. Thank you so much for calling my attention to that. I'm not hearing my chime for some reason. Okay. So, wow. B is a mess. Let me do this real quick because B is such a gigantic mess. Okay, so our function was this. Okay, it was a base to a constant exponent. Anytime you have a base to a constant exponent, you're going to follow power rule. I don't care what the base is. I don't care. But if you have a base to a constant x, you're going to follow the power rule. It just so happens that our base had a log function in it. That does not change the fact that we're going to do power rule. So when I go to do this derivative, I'm doing power rule. Power rule says you take the exponent, you drop it down to the front. You rewrite your base no matter what it is. You're going to rewrite that. And then I need to tack on the derivative of the base. If my base is a plain x, the derivative is just 1, so we don't have to really do that. But in this case, my base is definitely not a plain x. My base is an ln of x, so I have to tack on the derivative of the base. Oh, and what I forget to do? I forgot in my power rule, when you drop that exponent down to the front, you have to decrease the exponent by 1. Okay, so that's what I did there. So I worked this problem the exact same way I would if my function had looked like this. If my function had been 5x minus 3 to the 4th, you would have been like, oh, you drop the exponent down to the front. You rewrite the base. You decrease the exponent by 1, and then you tack on the derivative of that linear base. It's the same idea, except now my base was a log function, so I'm going to follow the log rule. And then Priscilla, the log rule is something you just have to memorize. It's one of the 5 rules that we memorize for this section. So the basic log rule says, if your function is ln of x, then the derivative is 1 over x. The more complicated log rule says if your function is taking the log of a composite function, oops, it's not picking up my stylus, then your derivative is 1 over the argument, which is the composite function, times the derivative of the argument. So these are just rules you're going to memorize, and I made that reference sheet that you can look back at while you're learning the material. So, I don't know, Jade, did that help you? And Priscilla, did that help? So Jade said yes. Priscilla, are we good? Got it? Okay, cool. Okay, so let's go back over here to our notes. Good questions. And thank you, y'all. If I'm missing something in the chat, please someone be brave and talk out loud so I can see it. Because I definitely, if you have these questions, I promise you, at least one other student has the questions, if not more. Oh no, my app closed down. Hold on real quick. Need to reopen my app. Okay, there it is. Share app. Okay, cool. So now these are more rules you're just going to memorize. So all these rules that I originally wrote here, these are all rules you need to memorize. And just heads up, the way I wrote them here, I only did it with like the generic x as the base. So look at that reference sheet for more detail about composite functions, okay? The reference sheet has more detail. I put these here just for us as a quick reference because we don't have them memorized yet, but definitely look at that reference sheet for more detail, okay? So print that out, If you haven't printed anything else this semester, print that out. Okay, so let's look at this function. Whoa, what's happening here? It looks horrible, right? So let's see. Here's my input. Where is my input going? My input's going to an exponent. It's going to exponents here, exponent. And the exponent is a plain x. It's a plain everyday x. It's not a composite function. I don't have, if it had looked like this, 2 to the x squared or something like that, minus 3 to the 5x minus 4. Like if my exponents had been functions, then we'd have to do chain rule. They're just x's here, so we don't have to do it. I'm still going to walk through the steps, so we don't have to. But here we go. So let's take the derivative. So what rule is that going to fit? So this rule, what's happening here is that your base is a constant. Both of these bases are constant, but your exponents are x's, right? So that's going to follow this rule right here. It's similar to the e to the x rule, but e is a specific number. Now your base is some constant number. It happens to be a 2 and a 3. So we're going to follow this rule here. So all I'm going to do is follow that rule. So here's what my rule says. And I have to follow the rule twice because the first term is following the b to the x rule. And the second term is going to follow the b to the x rule. Okay, so let's follow that rule. What does the rule say? The rule says if your function is b to the x, then the derivative is b to the x. Does not look similar as if your function is e to the x, then the derivative is e to the x? Does not look so similar? But we have to tack on the natural log of the base, which we're doing here. The natural log of e just happens to be 1, so we don't have to write it. So this is the generic form of the exponential rule. So let's go ahead and do this. Okay, so for my first term, if my term is 2 to the x, then the derivative is 2 to the x. But I have to tack on the natural log of the base, which happens to be a 2. And technically, I have to tack on the derivative of the exponent, but the exponent is a plain old x, so the derivative is a 1, so I don't need it. Okay, and then I just have to repeat it for the next term. Okay, the next term is 3 to the x. If my term is 3 to the x, then the derivative is 3 to the x. But then I have to tack on the natural log of the base, which happens to be a 3. So I'd write 3 to the x, tack on the natural log of the base, which happens to be a 3. And technically, the chain rule says take the derivative of the exponent, but that's just a 1 because it's a plain x, so we don't need it. So this is as good as I get. You don't have to clean that up. You don't have to be a hero and do fancy algebra. You can stop here. We just followed our rule, then we stopped. So how are you feeling on that? Show me a status. You have to pick out the rule that your function is going to follow, and then you follow the rule. Okay, we're going to get practice. Don't worry. Let's do some more. We're going to practice. The most important thing is figure out what rule am I supposed to be following, right? So what rule? I don't know. Let's look at this next one. Okay, 4. Here they're asking me to find the derivative, the change in y over the change in x, the rise over the run. Okay, we're asked to find the derivative. For this equation, technically it's not a function because they use the y equals, it's an equation, and it has a LOG in it. So I'm going to go immediately to my LOG rule. That's the rule I'm going to use. This rule is set up, the generic rule is set up when you have a plain x as your argument. And the rule says you send 1 over the argument, right? But the rule also has that you need to take 1 over the natural log of the base, whatever your base is. And then you tack on the derivative of the argument. So let's do all that. Of course, we could, oh wait, y'all liked the algebra rule, right? This is one where you could do it 2 ways. I'm going to do it both ways. But we could use an algebra rule for this. Let's start by doing that. So method number 1. Let's use log rule from algebra. Let's do our log rule from algebra. The log rule from algebra says if your log has an argument to the fifth that's raised to an exponent, so remember your argument here is x to the fifth. If that's the case, then the algebra rule from algebra says you can take the exponent from the argument and drop it in front of the log. So I'm leaving it y equals, because this is algebra, this is not calculus. And I'm going to drop the exponent in front of my log, and then I just have log base 4 of x. And now it more closely fits my generic log rule, because now my argument is a plain x. I don't need the chain rule anymore. I can still do the chain rule, I just don't need it. Okay, y'all, hold on. There's a car parked out in front of my house. Y'all, I've turned into one of those like old neighbors that shakes their cane. Now that I'm home all the time, I'm like, what is happening in the neighborhood? And someone is peeking their head out of a like sunroof, and they're right. What is happening? Hold on real quick. Y'all, there is someone just staring. Okay. I don't know. It's not. It's one car parked right in front of my house, and the person is standing up with their head stuck out of the sunroof, just staring at my house. It's freaking me out, guys. Okay, sorry. I'm trying. I know. This is what happens when you're like stuck at home in a pandemic. I just stare back. Oh, that's funny. Oh my God. I'm becoming a Karen. I don't know. Well, it's just they've been out there for a while, so I was ignoring it at first, right? And then they slowly, like a groundhog coming out of a hole from the ground, like slowly peeked their head up through the sunroof, and they're still there, just staring directly at my house through a sunroof, and they have not moved. Okay, I'm sorry. I'm trying to focus. I have to go out there, right? Like, I can't just let them continue to stare at my house with... Okay, I have to. Okay, no, I have... Y'all would go out there. Do y'all mind if I just go see what in the world is happening? Yeah, I'm going to bring my iPad. I'm going to bring my tablet and turn my camera on so you can be my witnesses. Okay. I'm going to be right back. I'm sorry, real quick. Our log rule says to do. So the log rule says, and technically, y'all, in the basic log rule, see how there's like an understood 1 in front of the LOG? In this basic log rule, there's an understood 1, and the 1 goes in the numerator. In that reference sheet, I put down if there's a constant in front of the log, that constant ends up in the numerator. It kind of just goes along for the ride. So technically here, my rule says I'm going to do my constant over the natural log of the base. The base is 4, so natural log of 4. And then 1 over the argument. The argument is a plain x, so just ends up 1 over plain x, times the derivative of the argument. But my argument is a plain x, so the derivative of a plain x is just 1, so we don't need to put it there. Okay. And then you can clean this up if you want. If you multiply straight across, you're going to get a 5 in the numerator. And technically, y'all, we don't write this ln of 4x like that because that x is not part of the argument. And see how that could get confusing? You could put the ln of 4 in parentheses if you wanted to, but typically what MyMathLab is going to do, and the standard in algebra, is that you'll move the x to the front. Since order doesn't matter in multiplication, you move the x to the front, and then you put the ln of 4 at the back. There we go. I mean, it's two like older white women out there talking to each other. I don't know why my brain went into crazy mode. They're still there. Oh, she just drove off. Okay, y'all, I can focus now. Okay. I'm losing my mind. Okay, here we go. So now let's do that same thing, but with the chain rule. Oh, wait, I don't know. Before I do this, does anyone have any desire to see the chain rule for this one? If you do, throw it in the chat. If you do, I will do it. Okay, Anastasia wants to see it. Okay, cool. I personally like chain rule because if on the day of the test you forget everything you ever knew, you know you can just fall back on the calculus rules you memorized, right? So we're going to get this same exact answer, but we're going to use chain rule. So now we're going to do the log rule with chain rule. So log rule with chain rule. Okay, here we go. So I'm going to rewrite my function here. And I'm going to emphasize that my argument is this x to the 5th power. Okay, so I'm going to jump right into my derivative. Oh, y'all. On method 1 down here where I use my derivative rule, see how I wrote y equals? No. Technically, you know, we are finding the derivative of that. So I should have done y prime, or they asked us to do the notation dy over dx. So I need to indicate that that's my derivative. Up here, this was still my original function, my original equation. So I used a y, but down here I took my derivative. So I had to change my notation to indicate that that's the derivative. Okay, cool. So now let's go ahead and do this. So I'm taking my derivative, so I'm going to do dy over dx, change in y over change in x. And my rule says, okay, let's use our rule. So now there's technically a 1 in front of the log, right? So when I come back up here to this rule, there's technically that 1 back there. So I'm just going to end up doing 1 over natural log of the base, which is 4. Then I do 1 over the argument, which is x to the 5th. Then I multiply by the derivative of the argument, which is x to the 5th. And then we got to clean all that up. Okay, so now algebra time. So dy over dx equals 1 over natural log of 4 times 1 over the argument times, I'm just going to do power rule over here, power rule. So that would be 5x to the 4th. Okay, technically that 5x to the 4th is over a 1. So when I go to do the algebra to clean all that up, let's see what it looks like. I'm going to end up with 5x to the 4th in the numerator, because I just did numerator times numerator times numerator. And then in the denominator, I'm going to write the x to the 5th first and the ln of 4 second. I'm just changing the order of multiplication. But remember, it's supposed to look like this one. So I just see here that I have x to the 4th in the numerator and x to the 5th in the denominator. So when those divide out, that's going to leave me just a 1x in the denominator. Oh, and that's ln of 4. Let me shrink all that real quick. I don't know. Maybe I like the method 2 better. I don't know. Maybe I like it better. Show me a status on how you're feeling with the, yeah, Arjana likes the chain rule. Michael likes the chain rule. Trinity likes it. Method 2 is better. What? Yay, calculus. Calculus for the win. I love it. Okay. Cool. I'll do chain rule from now on. Okay. Cool. So we're going to do a couple more of these. We're going to go a little bit faster through them so we can make sure we get to those word problems. Okay, here we go, y'all. So let's look at this. Now this one's tricky trickster, y'all. Normally what I would do is I'd let you try this and struggle through it, but I'm going to talk it out since we don't have that much time. It's an equation with 3 pieces. And we're going to find the derivative, and each piece could possibly follow a different rule. So let's look at the first piece here. E to the 3. Now, this is the super tempting thing I see people do. We know that if y equals e to the x, then the derivative is e to the x, right? We know that. Okay. But does that say y, does that say e to the x? No. Remember, e is just, if we have e to the 3, e is just the number 2.71 or 81, I don't know, it's a constant number. So this is just a constant. And what's the derivative of a constant? 0. There's no variable component in that. E is a constant irrational number and 3 is a constant. So that's just 0. So you don't really need to write it, but I'm going to write it for teaching purposes. Then we have this next piece here. We're going to follow the b to the x rule on that. And it's a plain x, so it's pretty straightforward. So I'm going to zoom out so I can see my b to the x rule here. So if my function is e as 3 to the x, my derivative is 3 to the x, but then I tack on the natural log of 3. Technically times the derivative of the exponent, but it's just a 1, so we don't write it. And then I'm adding, this last piece has an ln of x, so I'm going to follow my ln rule. And it's the basic ln rule here. So it's this one down here. The rule says that if there's a constant in front of the natural log, the constant ends up in the numerator. I have a 3 in front, so the 3 is going to end up in the numerator. So that's just 3 to the x. 3 over x. 3 over x. That constant ended up in the numerator. Or you could write it as 3 times 1 over x, but it's that 3 is still going to end up in the numerator. And then you're done. That's your derivative. Tricky, right? I know, with that constant. We're just slowing our brain down to read things. Okay. Now let's do number 6. Because 6 is another tricky one. Because here's the deal. Later on, really not till we get to test 4, but in test 4, you're going to see some pretty complicated business functions that you do not have to memorize. They're going to be given to you, but you have to know how to read them. And they're going to have e's all over the place. And sometimes the e's are going to be constants, and sometimes the e's are going to be exponential like functions. So you have to slow your brain down and ask yourself, where's the input going? So when I look at 6, this is what I'm saying in my brain. I'm saying, okay, here's 6. Here's my input. I'm inputting an x. In the first term, where is my input going? It's going to the exponent. So I'm going to follow the e to the x rule here. So for the first one, the e to the x rule says, if it's 2e to the x, the derivative is going to be 2e to the x. Super straightforward. Okay. Now let's look at the second term. Where is that x input going in the second term? See how that's going to the base? And then the exponent is a constant number because it's e is a constant. If that's true, you need to follow the power rule. If you have a base to a constant exponent, you're going to follow the power rule, which is nasty for this one. Oh, something in the chat. I heard it that time. Oh, I'm not seeing anything. Sorry, I thought I heard something in the chat. Okay. So because my input went to the base and because the exponent is constant, we're going to follow the power rule. So what does the power rule says? It says you drop the exponent down to the front. So wait, before I do that, if I had given you minus 7x squared, you would have been like, oh, power rule, no problem, right? You would have said, okay, we're going to drop the exponent down to the front, that's negative 14, rewrite the base, decrease the exponent by 1, tack on the derivative of the base, which is just a 1. Like you wouldn't have thought twice about it. The only difference is instead of putting a 2 as my exponent, I'm replacing that exponent with an e. That's it. You're going to follow all the same steps. So we're going to drop the exponent in front and multiply it with a 7. So that's going to give you minus 7e. Side by side is multiplying. I'm going to rewrite the base, x. I'm going to decrease that exponent by 1. And technically, we're tacking on the derivative of the base, but it's a plain x, which is a derivative of 1, so we don't write it. So how do you feel about the fact that we needed power rule for that second term? Are there any questions why I use power rule there? You got to slow your brain down and read the notation. Okay, and then e to the fourth, is there any exponent in there? Nope, that's a constant. If it's a constant, the derivative of that would be 0. And then I'm subtracting ln of e squared. Do you see a variable anywhere in there? No, it's a whole bunch of constants. That's a constant. I could plug that in my calculator and get a yucky decimal number, so that's also a 0. So your derivative for this one is just 2e to the x minus 7ex e to the minus 1. And you do not have to do any algebra on that. Okay, y'all feeling okay? So what's going to happen since we only have 10 minutes left is I'm going to write this one up in the answer key, but I'm not going to do it right now because I think y'all could do it, but it'll be in the answer key. Okay, and after class I can do it, but I want to jump down here to some word problems to make sure we have time to do the word problems. And I'm actually going to start with number 9 because it's the most important because it has a log rule in it, and then we're going to work our way back up to 8. So we're going to jump around. We're going to go to 9 and then back to 8. So let's look at 9. Okay. A statistician used data from the U.S. Census to construct this model. Okay, so I'm going to rewrite my model because remember, whenever you have a function, you have to slow your brain down and ask yourself what's coming in, what's coming out. What's the input? What's the output? So it says where S of t is the number of cable TV subscribers in millions. So I'm calculating my output is number of cable TV subscribers in millions. That's what we're calculating. So S of t is the number of TV subscribers in year t, where t corresponds to 1980. So I'm plugging in, my input is a year. And t equals 0 is the year 1980. So I'm plugging in a year, it's calculating number of TV subscribers. So it says two things. It asks us to use this model to estimate the number of TV subscribers in 2015. So there, we're just going to straight up plug in year 2015 into the regular S function and get an output. But then it asks us to find the rate of change of the number of subscribers. The rate of change of the number of subscribers. So then we need to find S prime and plug in the year 2015 and figure that out. So first of all, what's the year 2015? What am I really going to plug in? Am I going to plug in 2015 into that? No, right? I'm not going to plug in 2015. I need to figure out how many years after 1980 2015 is. Yeah, so how many years is that when we do the subtraction? It's going to be 35? Yeah, 35. 35, yes. So we're actually plugging in 35 years as my input. So let's go ahead and do that for this first one, 35 years. So 21, God, that 21's throwing me off there. It looks like an L or something, but it's the number 21, natural log of t plus 2. And I'm just going to plug in a 35 there. And just put all of this in your calculator and see what number comes out. So try putting that in your calculator. I'm going to put it in my calculator and we'll see what number comes out. (21) natural log of 35 plus 2. And I got this yucky number. Oops. I got 76. I'm going to round that to 76.7 because it says to the 10th of a million, round to the 10th of a million. So I'm going to round that to 76.7. And I'm going to interpret that in a minute. But before I interpret that, let's find the derivative and then we can plug 35 into it. So first of all, let's find our generic derivative of our function. So let me write our original function here, and then we'll find the derivative of it. Okay, so in this first piece, I'm going to have to follow the ln rule. And the second piece is a constant. Okay. So when I go to take the derivative, I'm going to follow my ln rule. It just so happens that my argument is a plain variable. So and there's a constant c in front that's going to end up in my numerator. So this 21, that 21 is going to end up in my numerator. So when I go to do this derivative, I'm going to end up getting 21 over the argument, which is t, times the derivative of the argument. But the derivative of a plain old variable is just 1. So you don't have to write that. And then plus 0, because the derivative of a constant is 0. So that's my derivative rule. Now I'm just going to plug 35 into that derivative rule and see what we get. .6. Okay, now interpreting this is kind of tricky, but before I interpret it, are there any questions how I got either of those two numbers? No? Okay, let's go ahead and interpret it. So when I interpret this, I'm going to say in 2015, because that's my input, right? You have to address your input and your output. In 2015, there are 76.7 million cable subscribers. Okay, that's just what my function told me. But my function told me how many cable subscribers. So there's that many cable subscribers, and the amount is increasing because I have a positive number over here. So the amount is increasing by what? You have to get your units going on here. Remember, a derivative is a slope. A slope is a rise over 1. You have to talk about the change in your outputs over the change in your input. That helps you get your units correct. So the output was number of subscribers. And what was I inputting into my function? What was going in? Years, right? So my input is year. So when I go to describe this number, it's going to be subscribers per year. So I'm going to say it's increasing by 0.6 million subscribers per year. Okay, heard the chat. Oh, yes, definitely, Michael. If you want to write that number out, that's even better. So Michael asked, can I expand this number out? So 0.6 million is 600,000. Like, if you know that, that's great. If not, my math hub will count it right. If you type, well, I think it'll count it right. Yeah, I'm pretty sure. If you type in 0.6 million, I will definitely count it right either way on a quiz or a test. Okay, we have 2 minutes left, and there's one more word problem I want to talk about. But before I move on, are there any other questions about this one? Okay, just remember, before I navigate away from this, when you're writing any kind of interpretation, and y'all saw on test 1, there were a lot of interpretations, and they weighed kind of heavily, you have to address the input and the outputs. And your derivative has to be a rate of change. So you have to have a per in there. You have to have 2 different units on that one. Okay, so let's look over here. So neither of these were the one I was thinking about, where we had to use the log rule. We're still going to do this one, but I thought I had one in here. Is there another problem that's missing? I thought there was one where you had to solve. Okay, I'll do it next class. No problem. It's not on your homework, I guess. It must be on the next homework. Sorry, I was thinking there was an equation that needed a log rule. But anywho, okay, here we go. So an internet store, my math lab cracks me up. An internet store sells blankets. If the store sells X blankets at a price of P dollars per blanket, then the price demand equation is this. Okay, so P is calculating the price at a given demand X. So X is the number of blankets. That's your demand, the number of blankets, and you're calculating the price at that demand level. Okay, and then it just says find both the price. So when it's asking you to find just the price, that's just a normal everyday P, and the rate of change of the price. So that's where you're having to find P prime. So this derivative looked kind of yucky, so I just want to do the derivative part real quick, and then I know you might have to go. So what rule is this supposed to be following? Where is my input going? My input's going to an exponent. The exponent has a constant base. So you're going to follow the b to the x rule. The b to the x rule here. So let's go ahead and follow that rule. When I take the derivative, again, if there's a constant in front of the b to the x, the constant just goes along for the ride. So this constant just goes along for the ride there. So I'm going to get 350. Then if the function's b to the x, the derivative is b to the x. So if my function is 0.99x, then the derivative has 0.99x. Then my rule says I tack on the natural log of the base. So I need natural log of the base. So I'm going to tack on natural log of my base here. And then technically I tack on the derivative of the exponent, but see how it's just a 1? It's just a 1 there. So I don't have to write it. So see how ugly this looks? Like it looks super hideous, but your base was just this ugly constant number. So I rewrote it base to the x, natural log of the base, just following this rule right here. And then after that, it's just plug and chug. So I know class is over. I'm going to keep going. If you need to log off, that is totally fine. You can log off. I'm just going to finish this problem up. And then if there's any questions, just email me. Okay, so let's go ahead and finish this problem up. Feel free to log off. Okay, so let's plug in. What are we doing here? It says find the rate of change. So we're finding the price when the demand is 800 blankets. So our demand is 800 blankets. That means we're just going to plug in. We just need to plug in x equals 800. So we can do that. So I'm going to put it into the original function, and I'm going to put it into the derivative. So I'm plugging it in my original function. I'm plugging it in this horrible looking derivative. I'm going to type really carefully on my calculator and see what I get for those. Okay, 157.2. Hopefully I did that right. Oh God, this is hideous. And then I got negative 0. I guess I'll round because it's money, but 5.6. So it's rounded. I don't know. Can anyone confirm those answers? Yes? Okay, cool. So now we just have to interpret it. So price, P is just the price per blanket in dollars. It's telling me up here, it's just in regular dollar. Oh my God, that's an expensive blanket. What kind of, this must be like a quilt, like something, I don't know. That's an expensive blanket. It must be out of spun gold or something, but we're just going to go with it. So we would say at a demand of 800 blankets, because that was my input, right? So at a demand of 800 blankets, that's my input. The price per blanket is $157.20. Gonna shrink all this so I have some more room to write. Okay, that's a crazy expensive blanket, and 800 people want it. Okay. So that's our demand there. And then we have to